All right. Well, welcome to the first astronomy club meeting, guys. Not the first for the leadership kids, but for the general people. Welcome. It's a new year, and we got our first guest speaker, Mr. Mike McKeag. He is going to talk a little about Dark Sky. He's a former Intel engineer, and he's a co-founder of the Oregon chapter of the International Dark Sky Association. He's also very interested in night sky photographer, or he's good at photography with night landscapes. So that's also a thing he does. And with that, we will turn it over to him to start our presentation for the night.
Yeah. So as was mentioned, I'm a longtime amateur astronomer and member of Rose City Astronomy Club, and then more recently co-founder and board member and director of IDA Oregon, the Oregon chapter of the International Dark Sky Association. And we're going to talk this evening about measuring night sky quality. And by quality meaning, the sort of lack of presence of the influence of artificial light at night. And this is an example of the night sky in the absence, pretty much the absence of artificial light. Other than that one tent in our campsite, which sort of graphically anchored this panorama of the Milky Way over the Alvord Desert. However, even at this remote location, that orange glow on the horizon to the left is from Boise, Idaho, about 130 miles away. And then over to the right, there's just under the clouds on the horizon, there's a little bit of an orange glow. That's in the direction of hang on a second while I move the zoom window out of my way, of Twin Falls, Idaho, about 200 miles to the east. So even in this nominally, I mean, a very dark Bortle 1 sky, the influence of artificial light still makes its presence known. Also note that in this dark location, the clouds are darker than the night sky, and we're going to see evidence later of how that's the reverse in locations that have a lot of artificial light on the ground that's being cast up to the. So here's another Milky Way panorama. This one is the Milky Way arched over the Dalles, Oregon, and the Milky Way is more muted in this circumstance, with so much light being cast into the sky by the lights on the ground in the Dalles. If you look carefully, you'll even notice two beams, like two searchlights, actually aimed at the sky. I haven't figured out what the source is yet. But anyway, you can see the influence of artificial light on our view of the night sky, and also notice that the hills are lit up by these lights as well. And now, upriver a ways at the John Day Dam, again we have the Milky Way, this time arched over the John Day Dam, which is unnecessarily very brightly lit up. And you can see how its light is cast onto the hills surrounding the river and the dam. And then, of course, we have Rufus, Oregon over here on far left. And then the glow along the skyline, those are the navigation warning lights of the wind towers. And so in this view, we have the Milky Way sort of faintly visible, outcompeted practically by all the light given off by the dam, a source of hydropower, a renewable energy source, and the glow of navigation lights on all these wind towers, a wind energy source. So the way I see this picture is just capturing renewable energy, which is going to be what we're going to have to depend on going forward. Therefore, a precious resource thoughtlessly squandered. So in reality, we have an entire universe right above our heads. But for most people, that view is lost in the glare of urban lights. Most people live in urban situations where this is the Dalles, Oregon, and you can see Mount Hood in the distance silhouetted against the glow of lights from Portland and other cities in the Willamette Valley. And then, in fact, at the very far left, you see a little bit of the light glow from the Central Oregon cities of Bend and Redmond. So these cities have impact far beyond their city limits. And then, of course, in the center of the view here again is the Dalles, Oregon. But this is what's above their heads. But for the residents of the Dalles and other cities, they can't see the rest of the universe. They're just lost in their own light dome. We can change that. It's as simple as changing a light bulb, a whole lot of light bulbs. And there's the challenge. Because to change those light bulbs, we also have to change minds. And you might ask, how many dark sky advocates does it take to change a light bulb? Many. And that's our task, is to change minds and change light bulbs. So for the balance of the talk, I'm going to explore some methods that we're employing to measure night sky quality, the brightness of the night sky, and distinguish between the sort of natural sources like the stars and gas clouds in the sky versus the illumination that's a result of our own artificial lights cast up into the sky. And there are two methods we'll explore. One is photometry, and we're employing a photometer made by a Canadian company, Unihedron, and we'll look into that in a little more detail, which is a meter that measures the brightness of the sky directly overhead in a small portion of the sky, about 20 degrees wide. And the way we're employing these meters, they're making measurements at every 5 minutes, night after night, week after week, month after month, year after year, from selected locations. Another approach is through photography. Using a digital camera with a fisheye lens, you can capture the entire sky in one image. And you can program a camera to collect those images at frequent intervals, night after night, or on selected nights. If it's a camera that's in a weatherproof housing, you could leave it out night after night. If not, you could just set it up for selected nights in locations of interest. It's also possible to produce quantitative sky brightness maps from a calibrated camera lens system, and we'll look at that in a bit. So here's the Unihedron sky quality meter. Through this is a lens, and then behind that is the actual photo sensor, and then a lot of electronics. And it also includes a fairly large capacity memory, so it can store, we probably could store well over a year's worth of data, making measurements every 5 minutes, every night of the year. And then it's battery powered. Our typical procedure is to put fresh batteries in, and it's about to be inserted in a weatherproof housing. And then just set it and forget it for 3 months, and then come back and pull the data off, connect it to a computer via USB, download the data, put fresh batteries in it, and set it up and let it go again. to make sure it's aimed at the zenith, it's mounted so that the window it peers through is level. Therefore, the optical axis of the sensor is vertical, pointing at the zenith. We have them now deployed at about 30 locations around Oregon. These are some snapshots of just a few of the locations. This map, the yellow stars mark the locations of the 30-some meters we currently have deployed. We started out in Central Oregon, so there's kind of a cluster in Central Oregon. And then some out in far northeast Oregon at Wallowa Lake State Park and at Halfway, and some in southeast Oregon. A couple now in southwest Oregon. We have some possibilities soon of some meters on the Oregon coast. Whoops, errant click. There is one out at Stubbs Stewart. And the green dots are some proposed locations, including one in Portland. And we're hoping that that first SQM in Portland ends up being on the roof of your school building. And then we also are working with the Gorge Commission to have a set that provide data for their environmental monitoring program. Oh, well, let me back up just a second. So we have hosts for all of these meters. Hopefully, perhaps your club will become a host for the first meter in Portland. And every 3 months, in fact, we have a data download week. In fact, this is our current data download week. And right now, hosts are pulling data off of their meters and then submitting the data files to us. And then we will analyze the data and produce a summary report. We do that twice a year, every 6 months. And we'll be looking at a lot of the contents of the most recent report that was issued a couple of months ago. So this is a graph of the readings from half a dozen meters at different locations in mostly Central Oregon on one particular night. This was the night of the 1st and 2nd of August, 2019. And these locations vary in how dark the sky is overhead. The red curve up here, well, let me explain. What you're seeing is a plot of sky brightness. And right here, the values drop very rapidly. That's evening twilight until you get to full dark at the end of astronomical twilight. And then it remains relatively constant through the night. And then at dawn, starting at the beginning of astronomical twilight, sky gets rapidly brighter again until sunrise. And then the vertical axis is a measure of sky brightness in magnitudes per square arc second, which is a measure of surface brightness that's commonly used by astronomers. And then the horizontal axis is time for one night, from evening till morning through the night. And this red curve is the data from a meter installed at the Hop Observatory on the east edge of Bend in a kind of a business district. So that sky there is pretty bright. This blue line is from Aubrey Butte on the west side of Bend, a residential area. And it's interesting to note that just in the distance across the width of Bend, in this business district versus a residential neighborhood, that there's a pretty significant change in the overhead sky brightness. And then these curves are from more rural locations. The yellow one is from the Oregon Observatory at Sun River. The light blue is from Prineville Reservoir State Park, south of Prineville. The kind of purple is from Pine Mountain Observatory. And then the darkest one, this green one, is from Indian Trail Spring, the location of the Oregon Star Party in the Ochiko Mountains east of Prineville. So all of this data is collected on the same night. You'll notice these two measurements from Bend. There was periods where there were sharp spikes in the record. That's due to passing clouds. And in fact, this is sort of illustrated by an all-sky camera that's mounted on the at the same location, on the Aubrey Butte location. It just captured some of the passing clouds. And notice that in this location, where an urban location where there's a lot of light from the ground being cast into the sky, it lights up the bases of the clouds, so the clouds are brighter than the sky. So every time a cloud passes over, you get an increase in the sky brightness until the cloud passes away. We'll see later that in dark locations, the reverse happens. So that's a snapshot of one night's worth of data. This is looking at a different night, but some of the same stations. This was a cloudy night in Central Oregon. You can just see how jagged the record is because of the variation in sky brightness as clouds are passing over the meter. And so here's a way, if you had all these graphs from all of these stations, one night after another, and you're trying to make sense out of that, it could be pretty challenging. So what we've done here is we've created a scatter plot, a density plot that takes all of the data from, this is from one station, this was the one on Aubrey Butte. And it takes all of the data that might be, well, this was data from April of 2019 through September of 2020. So well over a year's worth of data, night after night after night, from dusk till dawn. So this is time for one night. There's midnight. And so time on the x-axis and sky brightness on the y-axis. And the color coding is based on the frequency at which there's a reading that falls in each one of these little cells of time and sky brightness. And so blue is sort of lower frequency of measurements, yellow is somewhat higher, and then red is the highest. And you notice that we've got this band here kind of along the bottom, the darkest readings that are due to clear sky nights, or at least clear sky directly overhead the meter when the measurement was made. And then all of this, brighter readings, this is when clouds were passing by. This is when the sky was clear. So it gives you kind of an idea when the sky is clear and cloud free, and of course, moon free and sun free. We only use data when the moon is 10 degrees below the horizon and the sun 18 degrees below the horizon. So it starts to give you like a fingerprint of the sky quality above Aubrey Butte. And then for comparison, this is the data for the Pine Mountain Observatory. The same, span of was July, December of 2019 to April, September of 2020. And this scale is the same, but notice how much darker it is above Pine Mountain Observatory. But also notice that the clear sky data is here, and the cloudy data that is down here, even darker than the clear sky. That's because there's an absence of artificial light being cast up into the sky at Pine Mountain. So in Pine Mountain Observatory, when a cloud passes by, it's dark. and it's backlit by the starry sky above it. And we'll see some later. We'll see some photographs that illustrate that. So now, if you took all of this, a bunch of the stations that have been active long enough, we've accumulated enough months and months of data. That same kind of scatter plot for there's the Observatory, and they're ordered from the brightest to the darkest. This is Hart Mountain and Summer Lake and Shooting Star Ranch and Malheur Field Station, the like. Notice that these dark sites, when clouds pass by the sky, the clouds are darker than the night sky above them. But then these brighter locations like Oregon Observatory and Sisters High School, Tethrill, Madras, Aubrey Butte, et cetera, when the clouds pass over, the sky is brighter. And also how each one of these places kind of has its own fingerprint when you take lots of data and display it this way. And then if we apply a digital filter to the data that detects places where the plot is jagged, and you're basically a moving averaging filter, and you set sort of a threshold, said when the filter reports a result greater than a certain threshold, filter out that data from the data set and then replot it. And now you've removed a lot of that cloudy sky data, except some places like here, some of these near, and I think what's happening is they had like very uniform clouds, like a fog layer. And so the sky was brighter because of the cloud or fog, but it was not varying over time. And so then a second filtering was just manually performed by selecting data that was due to clouds, but the clouds were like a continuous sheet. And now you've got data that just represents the characteristic cloud-free, sun-free, moon-free night sky, the clear night sky at each of these sites. And then you can represent this data as, say, a box plot, which makes it a little easier to compare their values. So there's Observatory, the brightest site, and Aubrey Butte, a couple of stations at Aubrey Butte, Madras, Tethros, Stubbs Stewart State Park out in the Coast Range, Sisters High School, and they're ordered from brightest to darkest. And you can see that with a year or more worth of data and some filtering to take out the effects of clouds and the sun and the moon, and that you get kind of the clear night sky quality, a kind of fingerprint for each one of these locations. So there's some other things happening in the sky that also influence these readings. One of them is the passage of the Milky Way across zenith. And so this is a fisheye photograph of the sky. This was over, well, this is when I was attending the Golden State Star Party back in July of 2019. This was held at a site near Aden, California, Northern California. And I had a camera with fisheye lens taking photographs every 5 minutes, mounted next to an SQM that was making zenith sky brightness measurements every 5 minutes. So I had both the photographic information, what's going on in the sky overhead, along with the SQM data. And I picked this frame was kind of at a time when the Milky Way is passing, moving across the sky, and it's sitting right there at zenith. And then this is the SQM data that was collected that night. And you can see it's, you'll notice that kind of cyan line, that's sunset. And then from there to this line, that's civil twilight. And then from here to there is nautical twilight. From here to there is is astronomical twilight. So this is sun at 0 degrees, -6, -12, -18. And you can notice how the sky brightness is just plunging during that period. And then when you get to -18 degrees, which I always thought end of astronomical twilight was sort of an arbitrary number, but looking at the sky brightness measurements, this typically happens on a clear night. It plunges and then it holds steady right at the knee of the curve, is just about there at -18 degrees sun angle, and then stays pretty constant through the night until now there's the beginning of astronomical dawn, and then it starts to turn up and then climb through the periods of dawn. This yellow curve is actually the sun angle indicated on this chart. This curve has been climbing through the night, and it reached kind of a maximum here, and then it started to fall down here. Of course, then we come, then the sun starts coming up, but that point right there is when this photograph was taken. That point was when the Milky Way had been moving across the sky, producing more and more influence on the portion of the sky the meter is monitoring, reaching a peak here, and then it would have started falling off again, except for dawn interrupted that. So let's see. Yeah. So now taking data from here's a selection of stations, and then developing an algorithm that calculates the position of the Milky Way in relative to zenith, and applying a correction factor for the influence of the Milky Way on the readings, and factoring the Milky Way passage influence out of the data. So now we've removed clouds and influence and also the Milky Way influence. So we have an even closer measure of the intrinsic sort of clear sky quality. And then these are little scatter plots of the resulting data for each of these stations month by month for a year. And then they're color coded by season. So green is fall, blue is winter, then red is spring, and yellow is summer, and then we go into fall and winter. One thing that is pretty common with many of these sites is it kind of oscillates with the seasons, being brighter, sky brighter in the winter, and a little darker in the summer. And the sites where this is most pronounced are sites that often are snow covered through the late fall and into the winter. And we think that it's the light being reflected off of the sky, off of the snow on the surface back at the sky. And in a light polluted location like Observatory, a lot of that light is coming directly from below, from artificial lights in the cities like Bend. But in a location like Prineville Reservoir State Park or Pine Mountain Observatory, probably the light that's being scattered back into the sky is actually light that originated from the stars overhead, being scattered off of the snow surface, and then it lights up the sky. So this could be due to actually, in a place like a dark sky place like this, it's all natural light at work. The other thing that we did, having filtered these other influences out, is just did a linear regression to see if there was a trend over time. And the trends are marked here in terms of percentage change per year. There isn't enough data over a long enough span of time to really make much of this at this point. But our intention is to have these sites continuously occupied for at least half a dozen years. And over that time span, we may start seeing meaningful trends in terms of the sky quality, sky brightness. when you filtered out all the noisy stuff, we'll see. This is a plot of solar flux from 2013 to 2021. This marks when we've had stations operating. And so our data so far has been during solar minimum, but now we're just at the beginning of an increase in solar activity. And that's going to introduce another sort of variable source of this, in this case, natural light in the sky. One of them being air glow. The sort of magenta and green bands you see streaking the sky, that's air glow. That's a chemoluminescence in the upper atmosphere. The source is compounds in the upper atmosphere that get pumped up by sunlight during the day, and then they fluoresce at night. And when I had no experience with air glow, I hadn't even heard of it. When I took this photograph and started processing it, I was baffled by what I was seeing. That was my introduction. So that can change very rapidly over the course of the night, and it can affect the readings as well as, and it will become more common as solar activity picks up in the coming, next few years of the solar cycle. Air glow will become more and more a factor. And the only way to take that into account would be monitoring the solar wind data from the satellites we have orbiting the Earth, and find that's another factor to confounding variable. Another one, of course, is aurora, which at our latitude, visible aurora is uncommon, though actually there have been many nights. In fact, this night, we had a star party at LIGO, Hanford, and we noticed kind of a gray haze to the north. And I set up a camera and took some all sky images. And sure enough, there was this green glow along the northern horizon. It was aurora that we're seeing, but naked eye, we just saw it as a gray haze. But on returning to the campground that we were camped at a few miles away, it brightened up, and it was naked eye visible as colors. And I hurriedly parked and got the camera out and took some photographs before it faded. But aurora obviously, could influence the readings, and hopefully aurora at low latitudes might become more common as the solar activity picks up. So you've seen some examples already of the value of not just having sky brightness data from the photometer in the graphs that it produces, but also having collected photographs of the night sky. And this is my setup in the meadow at home here, the SQM, and then I've mounted a DSLR with a fisheye lens aimed at zenith. By convention, I always arrange the camera so that the top of the camera is north, so that north is at the top of the images in the end. And then the camera intervalometer is programmed so it takes like a 30-second exposure every 5 minutes, in sync with the cadence of photometer measurements. So what we've done here is we've created a graphic that synchronizes. You have the plot of the zenith sky brightness measured by the SQM. That's the red curve down below, with sky brightness in the y-axis and time on the x-axis. And then we have the all sky images that were taken at the same time as the measurements at every 5 minutes. This data was collected at South Steens Campground. It's on the west side of Steens Mountain and north and south of French Glen. A dark site, but you're going to see when I start to play. So we created this video, and I'll start it running, and you will see time advancing, and that vertical bar is showing where we are on the SQM readings. And you're watching images of the night sky, and you're watching the Milky Way rotating overhead as the Earth turns. Now we're seeing clouds arrive, and notice what the zenith sky brightness value does. It pretty soon is going to really plunge as the clouds practically cover the whole sky. But you see it's backlit by the starry sky above, trying to shine through the clouds. This is a dark site with no artificial light. And now the sky starts to clear, and you see the Milky Way. The bright object to the left is the Pleiades star cluster just starting to appear. But also notice a kind of greenish glow of the sky, and that's air glow. And as the if you look very closely, passing through the Pleiades and arcing down low, there's kind of a very faint brightish band. That's Gegenschein. And pretty soon, as we get closer to dawn, you'll see the zodiacal light become very obvious. That's all sunlight scattered off dust concentrated in the orbital plane of the solar system. And now the sky gets darker, though it's harder to see in the image. And I think what happened was the sky glow diminished. Now you can start to see the zodiacal light, just this pyramid of light scattered off dust particles, sunlight. And now we see dawn approaching. And then it ends at the end of astronomical twilight. And then you can play around. You can go put this wherever you're interested in studying it, and see what's going on in the sky relative. Like here we are. Let's get it back here in time to that very darkest point. Now with the combination of the photography and the SQM readings, you can see what's happening in the sky and understand the phenomena that are responsible for the variations as well. It's also possible with the data you can collect with a DSLR with a fisheye lens to produce quantitative sky brightness maps. This is the top frame is the original image, but it's been remapped from the polar coordinate, frame of reference of the original fisheye image to rectangular coordinates, with the vertical axis being elevation angle and the horizontal axis being azimuth. But it's the same information, just transformed to a different coordinate system. And you can see kind of what in the fisheye view was a straight line of the Milky Way across the sky now gets transformed into this arc. And then you can see the glow on the horizon of distant cities. This data was collected in Europe. I think, these marks are some of the cities. This is Vienna, the glow from Vienna, and then some other cities. And then this lower is when you take that raw photographic data and you translate it into the equivalent luminance. In this case, it's luminance in millicandelas per square meter, just another measure of surface brightness. And so what was qualitative photographic data now becomes quantitative measures of luminance. This data was produced using, well, first of all, the lens and camera had to be calibrated in a laboratory. And then that work is done by Andrej Mohar with Euromix in Ljubljana, Slovenia. And then he created the software that processes the images as well. So far, he's been limited to working with raw data from Canon DSLRs, but I've inspired him to work on creating support for Nikon. It turned out when I did a search of my image library, I had many thousands, maybe approaching 10,000 all sky images taken with a Nikon body with a fisheye lens. And he got excited about the research potential of that trove of data. So he's been motivated to work on being able to do this with the data from Nikon cameras as well. So that would put in reach doing actual quantitative mapping, not only of those using Canon, but hopefully soon Nikon as well. One other project we have going is to do something similar, but rather than using a DSLR whose sensor is at whatever ambient temperature is, using a cooled CMOS astronomical camera. And so now you have a Peltier cooler that you can just set the sensor temperature at some low temperature and reduce the sensor noise. So this is what we're using is a ZWO ASI 294 MC Pro. And here I was just kind of setting stuff up to see how we're going to mount it in the field. And then the lens camera calibration in a lab will be done by Dan Dorisco and Simon Baum at Night Sky Metrics in California. The camera control and image acquisition, and also hopefully the processing to produce the maps as well would be done on a Raspberry Pi. Here I was just figuring out how we might mount things in the field on this is the Raspberry Pi in this housing. We'll probably be adapting software created by Zoltan Kolanth in the Department of Physics at Etbos-Lorland University. And I'm working with Safan Klahane, who's a sort of semi-retired from the Pan-STARRS Near-Earth Object Search Observatory. She's spent her career writing software for astronomy, image processing, and the like. So this sort of thing's child's play for her. I keep swinging. All right, so, and it'll include an integrated GPS, temperature, humidity, and IR sensors, and we should be able to control it in the field from a smartphone or a tablet via a Wi-Fi connection with the Raspberry Pi, and then hopefully be able to power it with a relatively lightweight lithium, battery. Probably the big power hog will be the sensor cooler on the camera. But the idea is that the whole kit will be easily carried in a pack, no more weight and bulk than a DSLR with lenses and that sort of thing. So you could put it on your back and set it up in even some remote location you had to hike into and collect sky map data. But some early work, this was an image captured with that camera. This was from the Alvord Desert. These this overlay is rings that mark the zenith angle in 10-degree increments. That was one little project, was just to actually measure the lens image geometry for this lens on this camera. Then also we measured just spots that do not include stars that are, cover the range of brightness from, bright to dark, but sky that doesn't include stars. And from that data, determine the signal to noise ratio. And there's a number of experiments at different gain.
Uh-oh, students, looks like Mike froze. He lives in Mosier, which is outside of Hood River, and sometimes his internet goes out. He warned me that might happen. But we can use this time, though, while he figures out how to get back online to see if you have any questions. You could put a question in the chat, or you could just turn on your microphone and ask me. And this is pretty advanced. Mike was a professional engineer for his career. But are you getting the basic idea? Any questions?
How are the locations for the SQM photometers selected?
Oh, well, that's a good question. He said they started around Bend, and that's because his coworkers on this live near Bend, and the University of Oregon Observatory is east of Bend. And then after that, like he did Wallowa Lake State Park last summer, they just added that one. He added that one partly because every summer I take Ida B. Wells High School students out to the Wallowas, where I have a little property, and we have a multi-day star party, and we do community service. And we're hoping maybe someday having a public observatory. And Mike was excited by that, so he joined us. And then he said, hey, why don't we try to get Wallowa Lake State Park to be the second state park in the state? Prineville Reservoir State Park near Bend was the first. And now he's just trying to expand it everywhere. And it's kind of where each of these sites need a host. And believe it or not, they don't have a host in Portland. And that's why I'm trying to convince the school district to let us put one on the roof. Excellent. Carol asks, what is the data going to be used for? Well, anybody want to guess? Let me throw that out there. What do you think Mike and the Oregon chapter of the International Dark Sky Association is going to use this data for? Anybody just pitch in if you have a guess. No worries about being wrong.
Maybe having like quantified data is helpful for lobbying.
Absolutely. So part of it is just pure science to document the dark sky. They've made some discoveries already, like the air glow effect, the aurora borealis effect, the effect of the Milky Way passing over the zenith. But they also want to document this to at least make sure that light pollution doesn't increase. Remember those graphs they did that showed like -2% to +8%? Mike doesn't think that data is presentable outside of an academic setting like this yet, because it's only a few years, but he wants to get 5, 6, 7, 8 more years on that. One of the reasons to involve young people. And then if we see trends going up, we could lobby the local governments to say light pollution is not only bad here, it's getting worse. And there's kind of two ideas there. One thing is that in urban areas, light pollution is already very severe, and it is bad for people like us who want to look at the night sky. But he's not talking about it in this talk. It's really a different talk. The light pollution has been tied to all kinds of environmental and even human health problems. And that's another thing, is to document light pollution in suburban and urban settings. Now, in a very dark setting, what any small light pollution there wouldn't affect the environment substantially or human health. But those are places where some of us feel philosophically we should take the darkest skies we have in our region, our state, and really protect those. So that's why he's looking at places that are all over the state. And in fact, if any one of you, in addition to getting one on top of our high school, like have a family cabin somewhere or a second home or a relative who would be interested in this that fits a blank spot on the map, there's a lot of people very interested in this. Good questions, everyone. Hey, does anybody, go ahead.
No?
Oh, are you back?
Yeah.
That's okay. We had a good talk.
So did I became aware that I cut out on basically the next to the, essentially the last slide.
Good. So sum it up for us, and then we'll take a few.
Well, I'm assuming it was a slide with a. I was talking about preliminary tests of this cooled CMOS camera.
Right.
Okay. All right. Yeah, we got to it, and then the very last slide is simply just some of the resources that I provided links to, which you've already put in the chat. And
I'll put them in the chat one more time for anyone who came. There's Mike's email address, and here are the links. So Mike, I know a question that a lot of these students have is, I care about the dark sky for a wide variety of reasons, but I'm just a high school kid. What can I do?
Well, there's lots of possibilities. I mean, one, of course, you know, if we get permission to mount an SQM on your building, then the students, the members of your astronomy club, will be the hosts responsible for maintaining that station. It'll become part of our network, and you know, at a minimum, the task is every 3 months transferring the data off of the meter and submitting it to IDA Oregon. We, among the links is a link to the page on the IDA Oregon website, the Oregon Sky Glow Measurement Network. When you go to that page, there's a description of that project, but there you'll find a link for downloading the PDF for the most recent report. And a number of the charts that I showed actually come from that report, but the report was really written also as a tutorial. And so you may find that, and also that's where all of the data that's collected from sites around the state will be pulled together and summarized. That comes out every 6 months. So, but there's more to be learned, you know, about how to treat the data, and there's opportunities for students who are interested in getting involved in some of that.
One of the things, Mike, that I think would be great is you and your co-investigators on this used a number of classic, excellent data analysis techniques that these students at this age, I think all of the students who are here have the intellectual capacity to learn that, but I don't think any of them have been exposed to much more than a simple scatter plot or bar graph. And
a potential future presentation might be from my colleague, Bill Kowalik. Bill is a retired geologist, and he's been applying a lot of the tools and methods that he used to employ to explore the earth underneath our feet to the sky over our heads. So a lot of, but we might find a focus, you know, where Bill might be able to put together a presentation, maybe aimed at potential projects that students could, data analysis projects that students could engage in. Another link in the set is build your own all sky camera. This is not a all sky camera intended for quantitative sky mapping. This is for collecting images. The original was created by a Aurora observer in the Yukon, but he published his project in one of these websites, where people publish projects, it's attracted so much attention that he's kept improving the software. And I noticed in visiting his site today, he's improved the quality of the how-to instructions. So I'd encourage, if anyone has thought it might be fun to build your own all-sky camera and controlled by a Raspberry Pi, to visit that site and take a look. Bill Kowalik has one operating connected to the internet from his house, and you'll see under educational all-sky camera project, that link will take you to a page where you can observe the night sky over Bill's house right now.
It's 8 o'clock, so I don't want to go too much longer, but students out there, do you have any other questions for Mike about anything that he touched on in here? I thought those photographs of the Milky Way that you had taken were just stunningly beautiful. Is that something that a student could learn to do?
Yeah.
And, with what sort of equipment would you need to do that? How much investment would we have to make? Or is that possible just with a digital single lens reflex our family might have around the house?
Yeah, a digital single lens reflex camera with live view would be preferable.
Sure.
I mean, some of the cheaper ones may not have live view, but and then for live, the reason I say live view is really helpful is one of the tasks that is a bit challenging at night is focus.
Sure.
And live view is helpful. And if your camera happens to have a fairly high resolution screen on the back, that's even better. But you can get by with whatever you start with what you got.
Sure.
But DSLR and then a wide angle lens.
And students, the school, Mr. Carlson, the photography teacher, has a number of those that he can loan. He can't loan them out during the school year because they're already loaned to students in photography. But 2 summers ago, before the pandemic, 2 students, Ori Friesen and Maxwell Siversboyce, some of you may remember those two, they borrowed cameras from the school photography class, which are not used in the summer. And they borrowed the equipment, the SQM equipment from Michael, and they did their own investigation and looking at the differences in sky quality between Ida B. Wells High School and Gabriel Park and their own homes in the neighborhood. And they went and put together a presentation, which was very good, that City of Portland planners who were writing the light pollution guidelines for the city of Portland were very impressed and included some of their work in their final report. So that was students from our school who influenced public policy. One idea that came out of that plan from the city of Portland is they made an urban dark sky reserve kind of up by the Hoyt Arboretum and Forest Park, which is fabulous. But a dream I have is a second urban dark sky reserve, because Gabriel Park already is a mediocre urban dark sky reserve. And then if we could make our school grounds one, and then maybe the neighborhood in between, we could have some dark sky right here in the city as well. There's so many opportunities for students who are interested in political action, in electronics work, building a camera, in optical work, and in analyzing data. And there's also in the art of taking the pictures. So we might have you back sometime, Mike, to talk about, give us a starter for those of us who have digital single lens reflex cameras or can borrow them, on how to begin to take those nightscape images, because those were really beautiful.
Yeah, I'd be happy to do that. One other possibility is conducting outdoor lighting surveys. We're doing that for the Oregon State Parks that are interested in, that are developing applications for a dark sky park certification, because that's a requirement of the application. But it might be interesting to do a lighting inventory of the outdoor lighting at the high school as it is today.
I think that would be great.
And basically what you need for that is some of the information you just record in a spreadsheet. Daytime and nighttime photographs of the light fixtures is part of that process. And then IDA Oregon did purchase a spectrometer, and so making spectrometer measurements of the light fixtures is another component of that. But we could.
There's so much to do. I want to answer Brennan's question. When do you think would be the earliest we could get the SQM meter on the school roof? I'm sorry, the news is bad. I've been working for 9 months with a Portland Public School official to get permission for Mike and I to go on the roof to scout a location. 9 months. I got an email from her yesterday that she's leaving Portland Public Schools. Today was her last day.
Oh, no.
She's handing it off to another bureaucrat. So that's like the worst news in the world. This is 9 months of bureaucrats working to get permission for 2 grown adults to go on the roof. So I may need to enlist some parents and students to lay a little pressure on them. Yeah, Ryan says, is there anything we can do as students? Let's talk about that. We should wrap this up. Those of you, I hope you all enjoyed this talk and learned a lot. I think that's true. It was a great talk, Mike. We really appreciate it. I do know that even with my background, though, I took a whole 2-page of notes of things I want to learn about more. And some of you are freshmen in high school and the oldest is a senior. I'm sure you have so many questions. So here's how the club might work, how it's worked in the past. Some of you may say, well, that was cool, but I'm not interested in more dark sky work right now. I'm more interested in something else, which is fine. We have other groups. But Evan and Kate are the vice presidents in charge of the dark sky group. So what we should do is, I think anyone who wants to continue on, I'll send an email to everyone who showed up. I have a record, who wants to continue with the dark sky group and meet with Kate and Evan and sort of decide what we as a school, what we as a group want to do. Start simple, low cost, low time investment, and do something easy and work from there. We can proceed with that. And Mike has already told me he'd be happy to provide us with the appropriate equipment if we get permission to go on the roof, when we get permission to go on the roof, and how-tos and advice otherwise. Sound good?
I have an SQM sitting in its box waiting.
He is. He's got the equipment. I'm going to talk to the principal tomorrow and see if we can't facilitate this process, because I think that'd be really great.
And also, I think we did provide my email address, so I'm quite happy to field questions if anyone wants to reach out via email.
You bet. Did everybody see in the chat right now, Michael McKeag at darksky.org? I am going to, though, probably not tonight because it's getting perilously close to my bedtime on a school night. I know the kids are going to stay up for 5 more hours, but I unless I'm going outside observing, I go to bed before 9. You will all get an email from me, everyone who attended, and I'm going to ask you if you want to stay involved in particular with the Dark Sky group, and then Kate and Evan will plan a meeting. But for now, why don't we all turn on our microphones and say thank you and clap for Michael. I know he put many hours of work just into this presentation, and it was so good, Michael. I really appreciate it. So everybody go ahead.
Well, thanks.
All right.
Thanks.
Thank you. Thank
Thank you.
you.
And thanks, students, for coming. It was so great to see the regulars and old timers, and so great to see some new faces to me. Always welcome to stop by room 207 if you haven't met me in person before, after school, lunch, say hello. And remember, Monday, a week from today, November 1st, after school, 3:30, leadership meeting, planning the direction of the club. You're all invited. All right. Good night, everybody. Thanks again, Mike.
You're welcome.
Thank you, Mike. Thank you all for coming.
You're welcome.
Thank you.
Thank you.
Look forward to working with you some more.
Bye, Mike.
Bye-bye.